All right, so last but not least, we have Annalise Rickman. She's going to be doing experiment 6, please, for group 3.
Okay, so I'm doing 2D conduction. So basically we're just going to have an aluminum plate, and each surface edge is going to have different conditions. I don't know why I can't say that. So the objectives of this experiment are to first estimate the time required for the plate to reach thermal equilibrium, determine the steady state temperature field, and then we're going to numerically predict the temperature field using a finite difference algorithm, and then you can compare that to the results you get doing the experiment. So the apparatus is you need an aluminum plate, electro-resistant heaters, an ice bath, a rheostat to control the heat flux, and a thermocouple to measure temperature at different nodes. So this is kind of a picture of the apparatus, and the initial temperature is starts out at T is equal to T naught. Surface 1 is heated to a temperature of TW1. Surface 2, it has a heat flux of Q2, and then surface 3 and 4 are insulated, and so they have no heat flux. And the basic equations that we're going to use are the 2D thermal energy equation, and on the left side it's a first order dt, or d temperature, d time, so you need one initial condition at time is equal to 0, and that's t equals t naught. And then on the right side is second order equations, and you need 2 boundary conditions, which are the surface temperatures at different locations. So to use the finite differencing method, basically to integrate that thermal energy equation, it's kind of complicated. So they use this method, and basically the first thing that you do is you need to define equally spaced intervals. So that's just delta x is equal to the length over the number of nodes minus 1. And then the same for delta y, and for the purpose of this experiment, delta x is going to be equal to delta y. And then you can define any grid point as I and j. So then you have approximations that they give you in the lab for the temperature with respect to x and y. And they also give you approximations for dt, d time. And putting all that together, you get that equation down there at the bottom for delta x is equal to delta y, and gamma is equal to thermal diffusivity times the change in time over the change in increments squared. So you can take that equation and do a bunch of stuff to it, and you get a system of equations that can be solved for temperature at any grid point at a specified time. And then you repeat it for different time levels to obtain a bunch of different equations so that you can find different temperatures at different locations at different times. So I have an example, and it's an aluminum plate, and they give you the thermal diffusivity, which is 0.835 centimeters squared per second. And the dimensions are a 40 by 40 centimeter plate, and they want the estimate for 5 seconds. So first you find gamma, which I got to be 0.04175, and then using the simplified heat energy equation, I applied it to nodes 1, 1, 1, 2, and 1, 3, and then turned it into this matrix that they gave me in the lab. And that basically you can solve for the temperatures at nodes 1, 1, 1, 2, and 1, 3, and then you can do the same thing for every other node on the aluminum plate, and that gives you all your temperatures. So for the actual experiment, basically you just measure initial temperature of the plate with a thermocouple, which is T naught. Clamp drain hoses on the ice baths after they're filled, or no, before they're filled, I guess. Fill ice baths with ice water and add water if you need to. And then Adjust the rheostat to 200 watts. Place the thermocouple near the center of the plate and record the time it takes to reach equilibrium, and then measure the temperature at each location over the plate surface and record, and then turn everything off and empty the ice bath. So basically, since all that is probably extremely confusing because I was confused reading it, basically you're going to predict the temperatures using the finite differencing method. So you're basically just integrating the 2D equation using stuff that they give you and then solving for it with the matrix. And then for the actual experiment, you just follow the procedure and measure different temperatures, and then you can compare the experimental and numerically predicted values to each other, and hopefully they're the same. Any questions?
I have totally lost it. Did you use MATLAB to determine that matrix?
I did not do anything with that matrix,
Okay.
but you can, it tells you how to do it in the thing.
What were some of the like lambda and stuff that was in that giant long equation?
Wait, what?
Where they had that really long equation at the bottom? I didn't see what K and lambda and stuff were.
A K is just, or K plus 1 over 2 is like the first time level, and then K plus 1 you do it again for the second time level. And
Okay,
then gamma is just an equation.
so K is like the initial time level?
Yeah.
Okay, got it.